What is a data scientist with David Morton?
The Azure DevOps Podcast is a show for developers and DevOps professionals shipping software using Microsoft technologies. Each show brings you hard-hitting interviews with industry experts, innovating better methods, and sharing success stories. Listen on to learn how to increase quality, ship quickly, and operate well. And now your host, Jeffrey Palermo.
Welcome to the show. I'm Jeffrey Palermo, your host for helping you and your teams move fast and deliver quality and run your software with confidence in Azure, all while using everything that the .NET ecosystem has to offer. The podcast is sponsored by ClearMeasure, a full-service software architecture and engineering firm that serves companies using .NET and Azure. ClearMeasure builds mission-critical software, rescues failing projects, and empowers software delivery with a proven approach. Quick announcement, we're in the second year of my architect and software leadership forums. Sign up for the next session are up. If you lead a software team directly in a technical lead or architect role, or if you're in the executive oversight role of a custom software team and you'd like to collaborate with other peers that are doing the same thing, then sign up at the link in the show notes. We focus on more direct technical topics with the architect forum and more leadership, oversight, and management topics with the Executive Software Leadership Forum. So glad to have you in there, and it's just really good, robust discussions. And for those looking for Programming with Palermo, my video podcast, you can just search for it in any of the directories and you'll be able to find it. My guest today on the show is David Morton. David is a technologist with extensive experience across various sectors, including retail, finance, consulting, energy, commodities trading. He's successfully contributed to companies of all sizes, from small startups to large enterprises with up to 60,000 employees. And he's renowned for his ability to simplify complex concepts and solutions. And he believes in using the most effective tool to address challenges effectively and elegantly. David, welcome to the show. How are you, sir?
I'm good. Thanks for having me.
Oh, my pleasure. My pleasure. You know, we've been doing this podcast for a long, long time, but it's been a while since we've had somebody with a machine learning and data scientist background on the show. So I'm excited to dig in there. But before we kind of go on, I always like to ask the guest, if you were to go back in time, what are the high points that maybe are responsible for steering you in this direction, resulting in you working on the type of work that you do today?
Sure. Well, I guess I'll start a long time ago when I was 8 years old, and I pulled apart our Atari 2600 and tried to figure out how it worked, put it back together, and lo and behold, it worked.
Nice.
And after that point, I was hooked on trying to figure out exactly how every little thing works. I'm just almost annoyingly curious. I want to know how everything works. I was at the doctor the other day. I was asking him all these questions. My wife had to shut me down. She's like, stop asking so many questions. So when I got to college, being interested in how things work, I wanted to look at psychology. So I went to psychology, got a degree in psychology after 4 years at Texas A&M, graduated in 2001. And then after that, had no idea what I was going to do. So I got a couple little odd jobs, but I probably should have paid attention to some of the signs that I had at that time that I should have been in computers. I was likely the only psychology major at A&M who had built his own computer and was running Linux on it. And I should have taken that as a hint at the time, but I was just not aware enough to realize that that's something I should do. So after I graduated, got a couple little odd jobs, found myself in internal auditing at Aaron's. And then one day I was in the break room, and this was back in the day when they would have the internet computers in the break room because nobody had cell phones with them.
Right.
And there was a guy there trying to fix it. He couldn't fix it. So I figured out what the problem was and I fixed it. Then I decided I'm going to go into IT. So I went into that through a series of other events. I ended up in software engineering at Aaron's and just haven't looked back. Ended up at Catapult for a while, went to a company called Liquid Frameworks, which is now called Field FX, I believe, or Field Now, maybe, might be what it's called. And then I worked at JP Morgan for a while, worked at Spot Traceability, which was a smaller startup as their sole developer on the back end, front end, and database. And then I moved over to Chevron as a machine learning engineer, and then finally data scientist now in the HR group at Chevron.
Awesome. Well, there are a lot of .NET developers who are listeners of this podcast, whether new developers all the way up to people leading .NET teams. And so from somebody who's in the trenches, is a data scientist, I'm looking at you, I don't see a white lab coat, but just for those people who don't literally, there's no definition that comes to mind. From somebody who is one, what is a data scientist?
Okay, the way I think of data science is it's heavy on analytics. So when you're building a piece of software, you're generally going to approach it in a very deterministic way. What are the business rules that we need to implement? How many users are we going to have so we know how to design the overall software? What technologies are good right now? Do I want to use, I don't know, do I want to use React, or what do I want to use for the front end? Is it going to be web or whatever? It's a lot of deterministic questions that you ask.
Mm-hmm.
But when you start to go into the data science realm, what you're starting to look at is statistical analyses of things so that you can make predictions and maybe diagnose certain issues in whatever field you're in. So a good example would be maybe an attrition model in HR. Almost every company out there is going to have some kind of attrition model where they're going to weigh a lot of different values together: the age of the person, how well have they been performing, what's their previous job history, et cetera, et cetera. They'll put all those things together to try and come up with a kind of a prediction of how many people we can expect to leave the company next year, which will inform the people in HR about how many people they're going to need to hire to replace those people so they can begin setting up their recruiting pipelines. So a lot of it comes down to statistical analysis and taking giant data frames and putting them together and sending them through various different algorithms, see what comes out the other side. It is not programming. And although we use programming tools to do the job. So, my bread and butter is Python for the last 5 years or so. After I kind of left the .NET area several years ago, but I use Python every day and I program in it and I'm very proficient in it. But I'm not using Python generally to build front ends or, database access or anything like that. I'm using it purely for analysis.
Gotcha. For analysis of existing data?
Yes. Well, and that is another, whether the data exists or not is one thing, and whether you can get to the data or not, that's another. So, a large part of the job often entails portions of data engineering as well, just trying to get the data from one place to another, clean it up so that it's in a position to be analyzed. If you have missing values or bad data in your pipeline somewhere, that's going to show up in a lot of these models, and it's going to be weird when it shows up. You're going to look at it, you're going to go, that does not seem right. And so some of the skill set is being able to go back and find, what is that outlier that I'm looking at? When I see that chart, why is there this giant spike in the middle that I just don't think should be there?
Yeah.
Where's that coming from? Hunting that down, figuring out why it's wrong. A lot of it is talking to the business to understand the business use case so that you can apply the rules that they have back to the data.
So I just made a connection with the word scientist because you said you were looking at something and you just had a gut reaction. That spike shouldn't be there. You're just on the fly. It sounds like you're coming up with a hypothesis, and then you're going in to investigate to see if there's any truth to just your gut reaction to it. Is that right?
Usually, yeah. A lot of times what will happen is it all starts with a hypothesis. Any science should start with a hypothesis. You have your hypothesis, and it's called the null hypothesis, which is the hypothesis that would be true should you not be able to disprove it. So if you think about it like this, if it's kind of like innocent until proven guilty in one way, right? The null hypothesis is that this person is innocent, but they must be proven guilty in order to be able to, say they're not innocent anymore. So Britney Spears just popped into my brain. If you've got that hypothesis, a lot of times it leads to other hypotheses down the line. So you'll start with one major hypothesis. One that I worked on recently is, what is the value add to this particular course that people are taking? Are we getting the return on our investment for paying for this education solution that we have that we're providing to our employees? So it's a multifaceted question. So I have to kind of explore the data. I've got to look at it and start thinking about it in terms of, the business as well. What exactly are we defining as a return here? How can I get that data together to get a quantifiable metric to be able to say, this is the return that we're getting? And then how can I pair that data with the investment? Who's taking the course? How much of the course have they taken? How do they rate the course when they were done? And it may take in a lot of other subsets of data. What's their general performance at the company? Are they getting promoted afterwards? What are people saying about them afterwards in their reviews? You put all of this stuff together, and your goal is to try and answer that simple question. And so a lot of the sub-hypotheses you may have in there is, I think that this is an important data point to try and measure this. And so you might go and you might look at that data and go, no, there's no correlation at all there. There's nothing about that data that may be correlated with this data over here. So I'm going to eliminate that from the set and try and find something else. So it is a lot of experimentation. And a lot of the work that we do it's not building a full-fledged application a lot of times. We're answering specific questions for the business when they come up with them.
So given that you use a lot of Python, would you say that in some cases you could answer those questions just with SQL queries?
Probably. A lot of them you can. In fact, if you look at, you've got Databricks out there, and Databricks is, it's a big data platform built on Spark. So it's got distributed execution of data queries and all of this kind of stuff. And one of the values of having something like that is that you can use SQL in Databricks. So you could pull it out and type a query and get back your results quickly on giant data sets that you wouldn't be able to operate on, say, your MacBook, because the data is just too big. So yeah, I mean, a lot of data analysis can simply be done in SQL. I would say for some of the more complex analyses, and it depends on what kind of model will, prove your point or disprove your point most effectively. Sometimes that's not optimal, but it's not unusual to attack a business problem and realize all you really need is an average. That there's not really nothing too complicated you need to do with certain sets of data, because sometimes it just speaks for itself.
Yeah. You use the term a couple times, model, and with the overloading of that term with the GPT models that are a lot of people are talking about, can you just help us decipher what that specifically is referring to?
That's a great question. I was confused about this when I moved over from software engineering for probably about a year. I was like, what is a model? So I'm going to use a metaphor that I've used before. A model is how your grandmother thinks about you, right? Everybody remembers when you were young, your grandmother thought about you in a particular way, but she would only see you every year or two, maybe. If she only ever saw you every year or two, when you're 10 years old, she might still think you are like an 8-year-old. Now that's a specific topic called model drift. So her model of you is her interpretation of how you are. And so a model in data science is an interpretation of how the real world is, and it's a mathematical representation. So models can be used for prediction, which is often what they're used for, where you basically say, given this set of data, so given that this person, I did one a few years ago on a COVID-19 analysis, given that this person lives in this state and the demographics of this state are laid out like this, and if you remember 2020, the politics of this state are like this, et cetera, how likely is this person, or how likely is each individual person in that county to have COVID right now? And you could put that into a data model and do a simple linear regression on it. And when you do the linear regression, you can make a prediction on when you think maybe it'll spike again, when you think, what you think they should have. When I did this study a few years ago, I found that Iowa was underreporting their numbers. And about 2 weeks after I made that discovery, there was an article on the news that came out that said Iowa admits to underreporting their numbers. So you can use data science to actually really kind of get into the weeds of a lot of the statistics that you may hear on the news. You can build a model around it and then do your own predictions so that you can actually see what the truth of the matter actually is.
Okay.
But in a nutshell, a model is I take in information and I give a prediction on the result. And unlike software development, where your result is usually very deterministic and you can verify that it's absolutely right every time, generally speaking, in data science, there's no such thing as a perfectly right answer.
Okay.
You are making your best guess.
But this is decidedly different from a GPT model, right?
Not really. Not really.
No.
No. A GPT model is very similar. The only difference with a GPT model is when you're inputting information into the model, the information that it's inputting is called the context. So you write something down into ChatGPT and it takes your words and it coordinates all of those words along with all the data that it's been trained on in the back end. And that model, which is that mathematical representation of essentially all the data that it's been trained on, will then try to propose a response to your query.
Okay.
And it'll start with a few words. And as it continues building its words, it's essentially like the auto predict that you have on your phone, only it's on steroids. So as it puts together all those words and chains them together, those words are turned into, they're quantified into what's called a vector database. And then those vectors are fed back in and it begins feeding you out another set of text that's given back to you that seems to make sense. Now, one way that it is also like other models is that most models are giant, complicated averaging machines, which is why when you ask ChatGPT a question, it gives you a very vanilla answer because it is an averaging machine, ultimately at its core. A GPT model is just a very, very expensive model, essentially.
So there are lots of .NET developers who haven't gone deep into just data or databases, and then there's others who are well versed in the Kimball method for data warehousing and the difference between OLTP, the online databases, and then the OLAP analysis databases. Still in SQL Server where you can see the data, you can query it all. But so in those, we call those models as well. Right, the data model for
it's a data model,
right? Yeah. So, can you illustrate when you might say, okay, I've got an OLAP database with a data model that can give me certain averages and queries. It can answer certain questions. I can get information from it, but okay, now that's no longer sufficient. I need to reach for or create a different model. How do you make that decision?
Sure. So let's say that you are running a business and you need to know what the cycles of your business are. You could go and let's say it's a retail business and you sell Christmas gadgets, right? Comes up to Christmas time and you could try and predict what your sales are going to be. But if you try to predict on your sales in December based on the previous 3 months, you're probably going to be undershooting.
Right.
And that's just because there's a seasonality to the data that's in there. Every year, you get a spike in your sales. And that's true for almost every retailer out there. And that's why we have it called Black Friday. In data science, you would do something like apply like an ANOVA model or something like that that can detect some of that seasonality and be able to adjust your prediction based on that. Another good option or another good example of where data science would be used is if you're trying to optimize a supply chain. So there's a lot of different ways that you can, try and decide what is the most efficient way to, handle this particular mail package or whatever. But when you're dealing with hundreds of thousands of packages, how do you put them together in such a way that you can spend the less fuel and get them there as quickly as possible? And that would be something called linear programming, which is another kind of model that you can do in data science, which, as a fun fact, got its start during World War II and was a US secret during World War II.
Hmm.
They didn't tell the Axis powers about it. And after the war, they went ahead and released the algorithm and how it works. And I believe the creator got an award from Harry Truman for wartime efforts for having done that. They used the model to optimize essentially the supply chain of soldiers overseas and to
Yeah.
be able to put people in the right positions.
Okay, but isn't that still a data model that's compatible with the OLAP methods that you could put in SQL Server?
If you want to write a giant SQL function for an ANOVA model,
Okay.
you probably could. You could certainly write one in some language. I haven't been on SQL Server in quite some time, so I don't know what languages they'll take. But
Or is this
if you
where
can,
do you need another? Is it kind of like an ETL where with that method you grab your data store and you transform it in this way and put it in yet another relational database that then you query a different way?
sometimes, I mean, if it's not just like the medallion architecture or something like that in data engineering, but usually with a lot of data science, you're going to take a small sample of the data, you're going to bring it in locally into a notebook, or you're going to run it in Azure Machine Learning or something like that, where you can do some larger analyses on it by combining the tables together and mixing data sets together to try and augment the data to be able to determine what's valuable, what's not valuable. It really is a lot of experimentation.
Okay.
Because I might try multiple different models. I might try like a random forest somewhere. I might try an XG boost. I might try, this other thing over here. And I might look at all of this and see what all the results are that they're giving me. And they may not give me any results. I might get to the end and just go, look, there's no way that we can predict this.
Mm-hmm.
There's no way that I can tell you what's going to happen in this scenario. But a lot of times we're able to kind of give a general set of parameters. We think that it's, 50% likely it's going to hit this number this month based on historical trends and analyses and stuff like that. But yeah, again, you could do data science in almost any technology. Obviously, some technologies are built, to handle that a little bit better.
Yep.
Just, syntactically. But you could certainly do data science in SQL.
So you said 50%. That seems like it's a big concept of a divide, whereas there's certain questions that you would ask a set of data, and no matter how many times you ask that question, you're going to get the same exact result, the same result to the query. And you could do math, you could extrapolate, average product sale over the last 10 years, and you could project it into the future. And because it's just math, you're going to get it's deterministic. But then then there's other things where there's no determinism, there's no exactness, and you're now in like probability land. Am I thinking about that correctly?
You are thinking about that right.
So where does that shift?
Yeah.
And how can someone recognize it?
Okay, so when you're dealing with something like a neural network, for example, I want you to imagine, if you will, and I'll come back around to this. Imagine, if you will, a landscape, and it's a hilly landscape, and it's perfectly 100% smooth. And you're a giant in the sky, and you drop a basketball down onto this landscape. Now, what's going to ultimately end up happening is that basketball is going to go into one of the valleys, and it's going to settle, and it's going to stop there. And that's what, in mathematical terms, if you were to take a three-dimensional structure and you were to map it out, you would be finding the minimum. Now, the problem is sometimes, given the way the data is laid out, you can have multiple minima throughout your entire data set. So let's say that you've got a big hilly landscape. If you drop it over here, it's going to land in one place. But if you drop it in another place, it's going to land and stop in another place. And it's going to give you a totally different answer. Now, where you are in the sky before you drop that ball, in most computer languages, they would call that the random seed. So there is a little bit of determinism that's built in, especially when people are trying to replicate or test their models, they might put a random seed in there that will, given the same data set, give them a deterministic answer. But usually most of the libraries that we use, they don't have a random, they don't force you to pick a random seed. So they will pick a random seed and run it through. You could see the effect of this in, if you remember a couple of years ago when Microsoft released their Sydney model.
Mm-hmm.
And there was that New York Times article where the guy got on New York Times, and suddenly, after he had talked to Sydney for a while, suddenly Sydney was, telling this guy to run away with her, abandon your wife and run away with me. And he's freaked out by this whole thing.
One of the current
right?
AI models that he was.
Well, they shut it down. They
Okay.
shut it down after that.
Okay.
Yeah. And I mean, the guy is like, this really freaked me out. Like, this was weird. Why is this computer model telling me to run off with it? I mean, it had clearly turned into the movie Her somehow. Now, as a machine learning engineer, as a data scientist, I would look at that and I would say, okay, this is what's happened. Somehow during this transaction, the context of where this model thought it was got stuck in a local minima somewhere around the land of sci-fi novels about computers that fall in love with people.
Okay.
And no matter what the guy did, he couldn't seem to get it out of there, because what he was trying to do, he's standing at the bottom of the valley. He's trying to kick that basketball back up the hill to get it to go somewhere else. But that basketball at that point had hit such a local minima that it was really not feasible for him to get Sydney to move on to another topic. So a lot of that has to do with kind of non-deterministic results in data. There's always a little bit of randomness that's thrown in. In fact, if you see somebody if you're doing a data science model and the only way you can get the result that invalidates your null hypothesis is to send in a specific random seed, then you haven't invalidated your null hypothesis. Because what you've done is you've prompted the computer to give you back the answer that you're looking for, as opposed to letting the computer decide and then maybe running it 10 or 12 times and seeing what the average of its responses are to make a decision on whether or not you actually have a good model or not. That's a rookie mistake that often gets made with building a model.
Where's the line where developers who are used to querying databases and even have a data warehouse and they're even familiar with the OLAP methods, but every bit of their analysis work, data analysis work, has been SQL queries? What signals could they recognize where, hey, maybe this problem is not best suited with just SQL queries and plotting it on a line graph and a trend, but maybe a better answer is going to come from shifting to a different model?
If you're writing a stored procedure in SQL that's 300 lines long and forces you to output 12 cursors, you might do better moving to something else. I mean, it's a very practical concern. Is the language and is the tooling in SQL sufficient to be able to attack the data from this angle? Another threshold could be, especially when you're talking about Microsoft SQL, how distributed are you able to make this? Can you distribute the load of doing the analysis to other processors or not? Can you can SQL do that? Can SQL handle the big data that might be necessary to build a massive model that might have terabytes upon terabytes of information in it? Can you handle that on the server? If not, you may need to move to another kind of option to do some of that data warehousing. Although I would say if you're handling, terabytes of information, you're probably already moved on from SQL for some other reasons. But I would say, for me, the question would be, what's the tool that I can use that'll get the job done and answer the question the business needs to answer? And I can usually tell when I'm coding, something about this is too complicated. I need to step back, reassess, figure out if there's another way that I can approach the problem. And oftentimes there is.
Mm-hmm.
Oftentimes there's a library made. I mean, there might even be a library in Python or something that can almost turnkey get you the solution. But if you were to try to replicate that in another environment, you'd be spending months trying to solve the question.
Okay. Now, this podcast is the Azure and DevOps podcast. So we always like to touch on the operational side of what we're doing. And with even with complex data warehousing queries that are deterministic, there can be, on the smaller scale, there can be automated tests that prove that, okay, it works and have some automated verification. But once we're beyond there, what is the method to create automated tests to verify that queries or your Python code against these other models doesn't have bugs?
So the way I've usually approached testing, and some people may hate me for this, but the way I've often approached testing is I'll do a little bit of TDD, and then at a certain point, once things are pretty stable, I'm mostly writing tests for the bugs.
Okay.
And if there's a bug, I will write the test to make sure that I don't have a regression, and therefore I can know that test has been, or that problem has been solved moving forward. The approach is not that much different with data science. There is the concept in data science that complicates the matter, which is the fact that the world is not a stagnant place. Mm-hmm. Things change in the world. So if I were to build a model that would be trying to predict, try to predict fashion trends or something for the next year or two, I can't go and pull data from 1952 and feed it into the model and expect it to tell me what clothes are going to look like in 2025, right? Because that's 1952. And if I trained my model on data that was made in 1952 and then I tried to apply it today, that wouldn't make any sense. I would need to have some kind of what they call ML ops, where I could take the data and I could find a way to retrain the model periodically or adjust it in some way so that it'll reflect the latest data. Then if I send in a prediction and it gets it completely and totally wrong, then I really do need to go back and say, okay, why is it getting this prediction so wrong? Because a lot of times, especially, let me back up. You could separate models into two types. You have supervised models and you have unsupervised models. With a supervised model is going to make a prediction, but you as the data scientist are going to know what the correct answer actually is. When you train the model, you withheld that answer from the model when you trained it. But then you ask it to predict what that answer is. And you measure how good your model is based on how far away or how close it is to the correct answer. Now, there are concerns when you're building this that you have to be careful about. There's overfitting and underfitting. You could underfit a model, which could be a straight line when it's supposed to be, represent a sine wave or something. You could underfit a model where it correctly predicts everything that is in the training data set, but you feed it new information and it goes haywire and it has no concept of how to categorize what you've just given it. But ultimately, a lot of times, the goal with data science is to you usually use statistics to measure the validity of the data itself or the validity of the prediction itself to make sure that the prediction is valuable for the business.
Okay. And you used a key word in that. That's super helpful. You used the word train. And so now, before the GPT wave came about 2 years ago with a big splash of ChatGPT, there was lots of work being done under the name machine learning, which is kind of the harbinger of all this. And so I just want to make sure when we're moving away from database type models, is there a middle ground before we get into the machine learning models that we train, or is that the transition?
So I don't think we're ever going to move away from database models.
Right. But with some problems need to be a
Yes.
non-relational database model.
Yes. When you don't know the answer to the question and you don't have the answer, or the answer is going to come at some time in the future and you're not a fortune teller, you're going to need an ML model to try and solve that question.
Got it. So,
ML models are used in stocks and trading all the time to try and predict where the stocks are going to go and maximize profit.
So as we I want every listener to have a good takeaway that they could maybe do in their team. And so if some of these problems kind of meet your criteria and they're just beating their head against massive store procedures and trying to figure out how to get then they're okay. I need to get into machine learning land.
Yeah.
And so now I need to create.
I can give a simple example.
Yeah. So what can they do with their own, not massive databases where then they need their own data center to, train this model, but what can they do? Yeah. On the small scale.
Okay. So this was probably one of the first models that I put together. And it's a fun one. So here's an activity that you could do. Let's imagine that you're working for a company that has an inventory of items. And that inventory of items has serial numbers on it that are formatted in a few different specific ways. Now, you have somebody who's going to be on a phone somewhere, and they're going to be entering in the serial number of each of these items by hand. But you need to warn that person when they fat-fingered something and the serial number doesn't match what it should be, or the format that it should be. Now, there's two ways you can approach this. You can either put in some regex somewhere, and you could say, these are the formats that we're accepting, and that's it, which might work for one or two clients. But as you begin to kind of expand that out and open it up for other people to use, a lot of them may not use that feature. They may not know how to put the regex in. So you're burdened to put the regex on there. The alternative is you can train a model by taking various different characteristics of the string, the length of the string, how many dashes there are, how many alpha characters, how many numeric characters, what are the groupings of those characters, how are those put together. You can build a model on that, and you can train a model that can then take in another string, and you would tokenize it. You would break it down into its component parts, so it would be numerical and not text-based anymore. You'd send it in the model, and you could have the model tell you whether or not this looks like a valid serial number that your company uses or not. And you could deploy that model into a place where you could have 400 companies that are all using that exact same model, or the exact same training for the model, if you will. And you would train that model on their data over and over and over again. And as you do so, you can help them to do some input validation on the back end. Typically, or on the front end, do some input validation on the front end. Typically, when you're doing that, though, you wouldn't do, say, like a phone number validation where you're forcing them to, 334 on all their phone numbers. You would probably warn them and say, hey, this doesn't look quite right. Why don't you double check it?
Yeah.
And if they want to double check it, if they do double check it and it's right, they'll continue putting it in. And the assumption behind the model there is that once they put that in, there will probably be more that are also like that one. And as the model gets retrained, it'll no longer raise an alert about that one.
Gotcha.
So you can do that using, if you want to grab a Python notebook, a Jupyter notebook, grab some Python, do a k-means or a k-nearest neighbors algorithm, and you can build an anomaly detection algorithm out of that relatively easily with some tools like scikit-learn.
Now, is the training of that going to actually happen? Like Azure supports Jupyter Notebook. Is it going to happen in Azure, or is it going to happen locally on your workstation?
For this particular use case, you could probably do it on either.
Okay.
Because the data that you're dealing with is not big enough.
Gotcha. So for the ones where you're doing it
your computer,
when you're doing it locally, what everybody has, developer grade laptops or whatnot. But when you're doing this locally, are those perfectly fine, or is that where, hey, it's going to be running for a few hours?
No, I mean, for some use cases, it's going to be perfectly normal. For other use cases, it's going to be much larger. So that's going to go to the number of features that you're going to have in your data set. So as you add features, which you could think of features as columns in your table
Mm-hmm.
in SQL, and you could think of your an individual sample as a row in your table. So as you add more features, and as you put those features into the model, that begins to take more memory. And then also, as you add more data, that also often begins to take more memory.
Mm-hmm.
So, a lot of people don't realize when ChatGPT 3 was trained, it used about the equivalent of 150 747 round trips from New York to Beijing.
Oh, sheesh.
It's a lot of energy to train these things, because the amount of data that they were using and the number of parameters they're using, that's why you see the 7 billion parameters, 13 billion parameters. The number of parameters that they're using are so enormous that there would be no possible way you could do it on your machine.
Right.
The only way you could do that is with some kind of massively distributed system where you have, thousands of computers all working in tandem to try and answer the question,
Gotcha.
to try and build that model.
So for your own work, were you able to do a ton of things on your own personal computer, or did you get a special computer with some intentional hardware?
No, I mean, they gave me, actually, I think they did give me a special computer with intentional hardware. Now I've got a Core i9, but it's like 4 years old now.
Mm-hmm.
And it does the job most of the time. But these days I'm usually spending my time in AML, spinning up compute there and running it there, because I can get a computer with 192 gigs of RAM and several nodes to operate on. So it speed things up a lot.
What was the AML?
Azure Machine Learning.
That's what I figured. Okay.
Azure Machine Learning. Yeah.
Because we've got two cloud providers that start with an A.
Yes, we do. We do.
Okay. For bigger models locally, have you ever been tempted? Is it ever a need? Are you tempted to get a computer with the latest NVIDIA GPU that can do some of these things, or is that just a distraction that's marketing on their end?
I would say it depends on what you want to do. I mean, getting a nice computer with a nice GPU, most of the new laptops are coming out with GPUs or with better GPUs than they used to.
Mm-hmm.
And with neural network chips, like, chips that are designed for machine learning specifically, you're starting to see that in phones.
Yeah.
I mean, it's insane, the kinds of things they're doing. My own personal computer, it's my, MacBook Air.
Right.
Just because I really don't like fans and they bother me when they're spinning. So right. I got a, top level MacBook Air, and I can run a small LLM on there. I can't train an LLM on there. That would be insane. But I can run a small LLM on there. I've processed DNA data on there before, making use of some of the multi-processing that Dask was able to offer me there. And, it really just depends on the use case. It really depends on how much data you need and how much data you have, whether you need to look at all the data or whether you need to just look at a sample of data.
Yeah. Well, it sounds like with your product serial number example, that's not anywhere close to a large language model. Would you call that a small language model, or what would be the correct term for that type of thing?
I would call it an anomaly detection model. Okay. Probably.
Special purpose.
So, yeah, I mean, it's special purpose. So, like, another example of one that I've done is, this was at Chevron. We have to make sure that the oil tanks don't have things like big old, chunks of water on the top of them that are weighing down the top of the oil tank. We need to make sure that the hatch on the top of the oil tank is closed. Mm-hmm. So one of the models that we built was designed to go out and identify the tanks, and then take that and send the image of that tank to another anomaly detection algorithm that would then scan the image and determine whether or not there's an open hatch or not, and give you, now it'll never say yes or no. It'll say, I'm 90% sure that you have an open hatch here.
Yeah.
And at that point, we could send somebody out to that specific place to go close the hatch and reduce loss.
Right.
So that's another kind of anomaly detection algorithm out there.
Okay. And so just so I understand, anomaly detection algorithm, is that the same technology as not a small language model, but it's like a micro language model? A single purpose,
I mean,
very few parameters?
Yeah, I mean, as far as model size, yes, it is still they're both models, but the
Same
output of those models
training
is completely
technology.
different. Kind of the same training technology.
Yeah.
Yeah. The difference with something like what I was doing is when I send in an image, I send in multiple images, and it's going to use a neural network to try and identify what the characteristics are of an anomaly.
Mm-hmm.
So this is essentially a supervised training model where I send it data and I say, this is an open hatch.
Yep.
And I'll send it several pictures of an open hatch. Then I'll say, this is what it looks like when water is on the roof. And I'll send it several pictures of that.
Yeah.
And then I'll send it a whole ton of them that say, these are normal.
Right.
These are fine. And then technically that's a classification model.
Okay.
But I'm using it as anomaly detection.
Okay.
So I feed the data in, and after it builds that model, it'll take the new unseen data, process it through, and it'll come up with a determination or various percentage weightings of what kind of thing is in this image based on what it's seen before.
Yeah.
At the root of all of this, a model is nothing really more or less. Oh yeah, it is less. A model is very similar to like a 1 or 2 year old,
mm-hmm.
right? You hold an apple up. You say, hey, kid, this is an apple. And they point at it, they go, apple. And you go, good. So you're rewarding them for that. And you set it aside. You get out another apple. You hold it up. What's that? This apple happens to be red. They look at it. They go, plum. You go, no, this is another apple. They go, oh, apple. And what they're doing mentally is they're building a model in their mind
mm-hmm.
of what are the characteristics of an apple.
Yeah.
So they can recognize it. And eventually you show them a pear and they get confused again because a pear kind of resembles an apple a little bit.
Mm-hmm.
And you explain to them that it's a pear, and they begin to learn the characteristics of pears.
Gotcha.
And as they grow and learn, their model internally, their brain becomes a model of the universe that tells them what's true and what's false,
mm-hmm.
or what's real and what's not real, which is why young children get scared, because their model is often, their early models are often unable to detect truth from fiction.
Mm-hmm.
And it's also why I think data science is so important, because when you get online, a lot of times you'll see a lot of statistics out there. A lot of those statistics are manipulated in ways to try and make you come to a specific conclusion.
Mm-hmm.
And if you have the tools at your disposal to be able to do the analysis yourself, a lot of times you can figure out where the spin is.
Nice.
And that's a lot of fun.
Well, as we wrap up here, there's probably a lot of listeners who've listened to this, and they are dealing with a problem where they're saying, yes, I need to use those tactics. I need to use those tools because I'm just banging my head against, what they're dealing with now. So how can they get your help, or how can they find, somebody that can do this to get help? So, I mean, I'm always there on LinkedIn. So that's probably the easiest way to get a hold of me right now. Every LinkedIn is linkedin.com/in/ and my little token after that is David M. Morton. M stands for Michael. So linkedin.com/David M. Morton. Maybe throw it in the show notes, maybe. Yep. It'll be there. And yeah, feel free to reach out, and I'd love to talk. Fantastic. Well, this was a really great master's level course that you gave us here on data science. We appreciate it. I'm always learning. We're all learning. Absolutely. Well, thanks for coming on the Azure and DevOps podcast and sharing with us what a data scientist is and all the thinking that goes into it. This was great. Yeah. Thanks for asking me. Oh, my pleasure. And until next time, keep shipping.
You've been listening to the Azure DevOps Podcast, a show for developers and DevOps professionals shipping software using Microsoft technologies. Go to www.azuredevops.show for show notes and other episodes. On behalf of your host, Jeffrey Palermo, and our sponsors, Thanks for listening, and may God bless you.